This is our fourth and final lesson for Calc AP for Chapter 1, where we're just reviewing some important issues that we'll need for calculus. And we're going to do quite a few things here today. We're going to look at logarithms, trigonometry, and geometry. Now in Math 12, you're going to take a whole chapter to look at logarithms. I just want to look over the important stuff we're going to need to get going. Exponentials and logarithms are inverse functions of each other. So take a look at this exponential function here, 10 to the x. If I was to go and put 4 into that machine, in other words, calculate 10 to the 4th, then the number that would come out, 10 to the 4th, is 10,000. You know, basically a 1 with 4 zeros on the end. And so you could say that f of 4 is equal to 10,000. Well, logarithms are designed to do that process in reverse. So if I was to do this logarithm, same base 10, and to try to find out, hey, what exponent could I put on a 10 to get to 10,000? Logarithms are the way to actually evaluate that. So I could take the number 10,000, put it into this machine, and it's then going to go and kick out a 4. So this g of 10,000, or in other words, you could say, hey, what's the log, using base 10 of 10,000? It's really just asking the question, what would be the exponent that you'd have to put on a 10 to get to 10,000? And the answer there is going to be 4. Trying a few other pairs of numbers out, if I was to put 2 into the function f of x, 10 to the 2, well, that would be 100. Or if I was to go and put that into the logarithm, if I was to go and say, hey, what's the logarithm, base 10, of 100, that's asking what would be an exponent you could put on 10 to reach a value of 100, and that answer is 2. And you can even work with negative exponents. You can say, hey, what's f of negative 3? Well, that would actually be 1 over 1,000. So that negative sign just says that the 10 to the 3 is on the other side of the fraction bar. Same thing here. I could say, oh, well, let's do a logarithm, base 10 logarithm of 1/10,000th. That's that decimal 001. And the answer to that, it's answering the question, what would be an exponent? What would be the exponent that you could put on a 10 to have a value of 1/10,000th? And the answer is negative 3. That's all logarithms are. They're just the inverse function, the reverse process of exponentials. Now, there are some handy little rules that you can use for logarithms, and you'll go over these a lot in your Math 12 course. Let's just go over them really quickly here, just so we can kind of get rolling with our AP Calc. The rules actually mirror the rules you know for exponent laws. So in, maybe grade 9, you learn that if you're going to multiply two powers together with the same base, like x cubed times x to the 4th, that would be x to the 7th. In other words, you're just actually going and adding up the exponents in order to find the answer. So the answer here is x to the a plus b. If it's dividing, well, that's just the reverse process. That's where you would say, oh, okay, that's x to the a minus b. You just subtract the exponents. Or if you have exponents stacked up on a power, then you can say, oh, well, let's just multiply those two exponents together. And logarithms, being the reverse process of exponentials, have the exact same log rules, but just written a different way. So there's a log rule here that says if you have the logarithm of some sort of product, you can break that up into two separate logarithms. You could say, hey, that's like doing the logarithm, same base, whatever that might be, of this first thing, x to the a, plus the logarithm of x to the b. So multiplication within the logarithm turns into addition outside of the logarithm. You might not see that as written as a power like that. You might just see it as factors. Maybe you'll see something that says, hey, what's the logarithm of c times d? Great, that's just the logarithm of c plus the logarithm of d. Division is just the reverse process. So if you're dividing, that turns into a subtraction. So this would be the log of x to the a, subtract the log of x to the b. So if you see a division within the question, it turns into a subtraction outside of the question, outside of the logarithm. This one here is a very, very handy log rule. If you ever have the log of a power, actually like we had on this top green line up here, you can actually take that exponent and you can pull it outside and put it just in front of the logarithm as multiply. So this turns into a times this logarithm of the x. Very handy way to pull exponents down to a place where you can access them. One last log rule, or maybe it's the hey, this isn't a log rule deal. Be careful with this one. Okay, the log of a sum. What's the log of a plus b? There is no rule for this. So don't try to create one. Okay, that's just kind of stuck at that point. But we do have rules for the logs of products and logs of quotients, but nothing for the log of a sum. Okay, on the next page, we're going to take a look at a couple things. The first one is something called the change in base formula. You can do logarithms of any kind of base. The other page we were doing base 10. You could do base 3, base 2, whatever you want. Probably the most popular base might be a number you haven't met yet. Its name is just called e, and it's a number between 2 and 3. It's irrational, just like pi is. So this number just keeps on going without any pattern. It kind of looks like there's like 2s and 1s and 8s repeating, but there's actually no pattern to it at all. And it's probably a number that's more important than pi in the math world. And we're going to often do exponentials with it, and then we're going to need to do logarithms with it. And you would think it would seem to make sense that you would call its logarithm a base e. That's kind of unclear. Let me do that again. A base e logarithm of whatever number you've got. But we actually give it a special name because it's so commonly used in math. It's so important to us. We actually write it like this. And the letters ln actually stand for, kind of in reverse order, natural logarithm. These exponentials written with that particular number e occur really often in the world of nature, in the world of physics, in biology, in chemistry. And so we just call it, the natural logarithm, and we'll use it all the time. It is by far the best base you can ever use for an exponent or for a logarithm. Now this last little thing here, this ln, is often just pronounced ln x. Okay, and that would be this most useful natural logarithm. Now you might have a question where it says, oh, can you figure something out base 3? Like actually down here when we do this example 3, there would be a moment where it would be kind of handy if I had a base 3 logarithm button on my calculator, but I do not. I only have 2 logarithm buttons on my TI-83. Base 10 one, which is here, and then this natural one, which is there. Some other calculators let you do other bases, but mine don't. And so you now have to have a plan for dealing with logarithms with weird bases. And here's the way out. This statement here, this log base a of x to come up with an answer of y, is equivalent, if I write it in exponential form, to this. If I take a base a and was to put the exponent y, which the logarithm found on it, it would have a value of x. And what I'm going to do now is just take a logarithm of that. And I don't want to take a logarithm base a because apparently that's some sort of awful base, right? So I'm unhappy about this number. Maybe it's a 3 or something weird. And I'd rather do a different logarithm, maybe a base 10 logarithm, or maybe even better yet, a natural logarithm. So I'm going to go and do a natural logarithm of both sides. I'm going to do it of that left-hand side, and I'm going to do it of the right-hand side. That's a fair thing to do. So there's my equation, and I'll have a to the y, and I'll have just the x right there. But on the previous page, we talked about how there's this rule that if you ever have an exponent inside your logarithm, you can drag it out front. Super useful because then you can get access to that exponent. So I'm going to do that here with this y. I can write this now as y multiplied by this logarithm of my choice. I'm going to choose to do a natural logarithm if I can. I like it, of a. And then over here, that same logarithm of my choice of x. Okay, well the whole goal was to come up with some way of expressing this thing y, right? Like how do you do this logarithm? But with better basis for your logarithm. So let's solve for y right now. I think we're ready to rewrite this. If you write that as y equals, because that's where we're at, y is equal to that log. Well, let's just solve for y by dividing by this natural logarithm of a. And so I have the nice logarithm of the number I was supposed to do, all divided by the nice logarithm of that awkward base. So I don't mind doing natural logarithms. I just don't want to do maybe like a base 3 logarithm. Now I'm going to sort of use that when I do this example on this page here where we're going to solve for x in this exponential equation. I'm going to actually kind of avoid it too, and then you'll see that it just naturally shows up anyways. So exponential equation, the variable that you're looking for is up in the exponent, and it's tricky to try to solve for those unless you have logarithms, but we do, so we're good. I'm going to access that 3 to the x by just slowly stripping things away, like this 2. Let's subtract 2 from both sides. 72 would be 4 times 3 to the x. Okay, getting closer. I cannot say this too many times. You cannot multiply the 4 and the 3 right now and say, oh, well, that's just 12 to the x. That violates the rules of order of operations. This exponent would have to happen well before the 4 comes in, so you can't multiply those. I could divide both sides by 4, and if I divide 72 by 4, I end up with 18, and that would equal 3 to the x. Now there's no nice number that lets me hit 18. You know, 3 squared is 9. 3 to the 3 cubed is 27, and I kind of missed the 18 in there. So there's no easy number to do for that x to get it to work, but maybe I can use logarithms to get there. I kind of want to do a base 3 logarithm of 18. You know, if you could do this, you'd be done. Because that pink expression there says, hey, why don't we go and find the value that you could put on a 3 to have a value of 18. I want that, but I don't have a base 3 logarithm on my TI-83. So I could do a logarithm of my choice. I'm going to do a natural logarithm. So I'm going to do a ln of 18, and I'm going to do a ln of 3 to the x. I'm going to do that to both sides. That seems fair. And there's that x up in the exponent again, inside the logarithm. I do not have to tolerate writing it like that. I can pull this x out front and then say, hey, that's like x times this nice natural logarithm of just a plain old 3. My calculator can do that. So when I solve for x, when I get x all by itself, I can say, yeah, we're done. This answer for x, it'll be this natural logarithm of 18, all divided by the natural logarithm of 3. And that doesn't reduce in any way. You can't say, oh, the lns cancel. You have to do those separately and then divide. But I can take my calculator and go, okay, hey, what's the ln of 18? And when you're done, can you divide by the ln of 3? So for AP Calculus, if you have a number like this that is irrational and keeps on going without any termination, you have to write down 4 decimal places. You don't have to worry about the number after it. You don't have to worry about rounding, but you have to at least go to 4. So 2.6309 would be an okay approximation. And if you think about it, it's kind of done this change in base formula up here, right? We've got this nice natural logarithm of the 18 divided by the nice logarithm of the 3. So the stuff that's in that big black box up there is really just saying, yeah, look, that's what you did right here. That's how you found the base 3 logarithm. Kind of happens naturally just when you take the logarithm of your choice of both sides. I'll always choose that natural logarithm. It's actually probably the best logarithm that you could ever do. So that finishes what we need to do with logarithms. Now what we're going to do is take a look at trigonometry. So just over the next page here, we'll see what we've got. So I firmly believe that the unit circle is your best friend for trigonometry. I know people go, oh no, it's like SOHCAHTOA. Well, SOHCAHTOA comes from this idea of the unit circle. You have to imagine that there's this giant Ferris wheel, and you're riding on there, and you begin right here. This is where the ride begins. That's going to be 0 degrees, and then we rotate counterclockwise. So this would be maybe 30 degrees. Here it could be 45 degrees, 60 degrees. I'm not going to write them all in, but maybe just a couple, right? 90. This would be 120 degrees and so on, right? 180 degrees out here. And the whole idea of the unit circle is that if this Ferris wheel happened to have a radius of one gigantic unit, right? That's this one right here. If you were to watch the x and y coordinates of that red dot, well, I guess it's orange before I covered it in red, as it moves around, you would be actually looking at the sine and the cosine for the particular angle you're at. So for example, at 30 degrees, if we wanted to look there, if you were to go and examine this point right there, okay, I'll draw it in red, if you were to go and look at its x value and at its y value at this moment, you could find the cosine and the sine for 30 degrees. And so the x value, it's around 0.86. It's actually an irrational number. It ends up being exactly root 3 over 2. That's the cosine of 30 degrees. And the y value, that one we can actually see nicely. It's exactly 0.5, if 1 would be all the way up there. So the sine of 30 degrees is going to be 1/2 because it's telling you about that y value of that point that I've drawn in there in red. Let's keep wandering around and look at some other interesting points. Another interesting one might be this one, 150 degrees. Also, still 30 degrees up from the x-axis, okay, just like this one was right here. Okay, well that one is going to have the exact same y value out there at 150 degrees. It's also got 0.5 for its sine, but its x value is similar to this last one, but it's going to be negative because the Ferris wheel is now hanging back to the left. Okay, let's go with the next one that kind of matches up with that. Let's go and take a look at this point right here, which would be 210 degrees. It's going to have a negative x value, right? Just looking at where it's located on that xy plane, it ends up also being minus root 3 over 2. And now its y value is negative. It's negative 1/2, negative 0.5. And the final one, you can probably imagine which one I'm going to look at. The final one I want to look at is right here at 330 degrees. You could also call it negative 30 degrees. That one there, if I look at the x and the y value for this point, I can see that the x value has gone back to being positive again. It's root 3 over 2, but the y value is still in the negatives. And that's the way you want to think about sine and cosine. So in Math 12, yeah, you're going to spend some time looking at the graph of cosine and the graph of sine. The graph of cosine is graphing the x value for that dot as it moves around. It starts here at the beginning, that's 0 degrees, so the x value would be 1, and then it wanders back to 0 for the x value, and then back to negative 1, up to 0, and then up to 1 again. So cosine, if you graph it all the way out to 360 degrees, would begin here up high at 1. By the time you get to 90 degrees on the Ferris wheel, your x value would be 0, right? You really just want to think, hey, what's the x value for a point right there? Well, the x value of that point is 0, right? That's what this graph is recording. Then at 180 degrees, the x value is negative 1. At 270, it's at 0. And 360, we're back to where we began. And it's this beautiful, gently curved graph like that. That's the graph of cosine. And the whole SOHCAHTOA thing comes from this, right? It's a consequence of this. So looking at the quadrants, we number them 1, 2, 3, and 4. If people were to ask you, well, where in those quadrants would you find positive cosine values? Well, whenever the x's are positive, that would be off here, you know, on this part of the page. So that would be quadrants 1 and quadrants 4. And yeah, sure, I know you maybe have a little way of remembering this from Math 11, but if you think of the Ferris wheel, it's pretty clear that it's positive there, and it's going to be negative here because it's about the x values. Sine, on the other hand, records the y value of that point as it wanders around the wheel. The y value begins at 0, and then at 90 degrees, when the Ferris wheel points straight up, the y value is 1. And then at 180 degrees, you're flat again. And at 270, you're hanging down. And at 360, you're back to 0 for the y value. So again, this gently curving graph like this. And if people ask, well, when is sine positive? Well, that's asking you, when is the y value of that point positive? Just think of the Ferris wheel rotating. That would be up here. So sine is going to be positive in these two quadrants. And you don't have to remember any little acronym, CAST or whatever. Just simply think about where these things are located and how cosine goes with x and how sine goes with y. Okay, on our little crash course of review, let's take a look at a neat little way for remembering special angles. So this is kind of a Math 11, Math 12 issue of special angles, but we just have to come up with some quick ways of remembering this. Here's one that I was shown. If you can count starting at 0, then you're in business. I'm just going to write down up here in my little row for sine, I'm going to write down the numbers 0, 1, 2, 3, and 4. And if I can do that, I've got this done. This works for sine. If you take a root of that and divide by 2, you'll see that, oh, okay, well, that's 0. Root that, divide by 2. Well, the root of 1 is 1. Okay, so that's a half. Root that and divide by 2. Okay, that just is what it is. It just sits there. Root that, divide by 2. Yep, okay, that's the sine of 60. And the root of that divided by 2. Well, the root of 4 is 2. Divided by 2 is a 1. So there's kind of a silly little way of figuring out what all the special values are for sine for the interesting angles up to 90. Now, cosine. This is no accident here with the way this works. The letters SIN are an abbreviation for the actual name, which is sine, and then COS is an abbreviation for cosine. And it's a cofunction, and there are 3 pairs of cofunctions here in trigonometry, and cofunctions work with complementary angles. In other words, angles that add up to 90 degrees. So 0 and 90 are complementary, 30 and 60 are complementary, and 45 and 45 are complementary. So the plan is this. For cosine, we just want to reverse everything. Okay? Whatever you had for sine, just reverse the plan in your table and you're good to go. So if you came up with a way of remembering what sine was going to do, then cosine is no problem at all. Cosine of 0, well, that's like the sine of 90. So as long as you know the sine of 90, you're ready to go. This is a 1. Somebody says, hey, what's the cosine of 30? You don't need to memorize that as long as you know the sine of 60. That's going to be root 3 over 2. Somebody says, what's the cosine of 45? I don't know. What's the sine of 45? Oh, I have a way of remembering that. It's root 2 over 2. Cosine of 60? Not a problem. Do the sine of 30 instead. It's a half. And then this last one here is 0. So that gets you at least the whole first quadrant done. And then we'll see at the bottom of this page ways that you can go and get any other quadrant ready to go. Next thing, reciprocal trig functions. First of all, why would you even want them? Well, let's say you're doing this question in Math 10, trying to figure out how long is h, how long is this hypotenuse. You might say, oh, well, let's use sine. It's probably a good move. So the sine of 20 degrees would be the opposite, 5 divided by h. And then as you go to solve this thing, you're going to have to multiply by h and divide by the sine of 20. So the answer is 5 all divided by the sine of 20 degrees. And you have this sine of 20 degrees that's down there in the denominator. You have to divide by it. And mathematicians wanted to come up with a nice little abbreviation for saying, hey, well, what's 1 divided by the sine of 20? What if I don't want to write this as a fraction? Is there a way that I can do it? Here's what you cannot do. You cannot say this. Well, for one thing, you can't even do that with a 20. But this does not mean sine upside down. That actually means the undoing, the reverse process of sine. So that option was off the table. So they came up with a different shorthand for doing this. And here it is. If you want to divide by sine, you can say, oh, that's cosecant. So I'd still have the 5 hanging around. But then I could say, oh yeah, cosecant of 20 degrees. And it's only there, its only purpose is so that I don't have to write a fraction. So the cosecant of an angle is really just 1 divided by the sine of an angle. That is not the same thing as what's up above the sine on your graphing calculator. This is the undoing of sine. What it's on the page here is just the reciprocal of sine. So that's why they're called reciprocal trig functions. There's one for cosine as well, and it's called secant. So the secant of an angle is just 1 divided by cosine, should you ever need to find that. And the third one is cotangent. The cotangent of an angle is 1 over tangent of an angle. Now, 2 little bits of trivia here that could just help you remember stuff. If you're trying to remember, like, oh, how am I going to know which one's which again? I always thought this was kind of neat. Just take a look at the second consonant. I might be spelling that wrong, but whatever. So cosecant, I see a C and an S. There's the second consonant in the name. It's an S. Yes, it's sine upside down. Second consonant here, well, S is the first, E is a vowel. There's a consonant. It is cosine upside down. And cotangent, C is a consonant, O is a vowel. There we go. Second consonant's a T. Tangent upside down. So that's a neat little way to remember it. And another thing is we now have 3 different kind of pairs of cofunctions. So cosecant. If somebody says, oh, gee, I need to do the cosecant of 20 degrees, and you're like, oh, I don't even know what that is. Well, maybe you know the secant of 70 degrees because they're going to be cofunctions. And tangent and cotangent do this as well. So if somebody asks you, oh, what's the cotangent of 30 degrees? You can say, I don't know, but you know what the tan of 60 is? Because they are complementary cofunctions. All right, last thing here on this page, let's take a look at how you can use reference angles to try to come up with a specific answer for one of those exact values. So somebody says, oh, you got to do the cosecant of 210 degrees. Here's what I would do. First of all, let's just make a little sketch of where this angle is. Where is 210 degrees? Well, 0, 90, 180, 210 is going to be down here like that. Okay, there's my 210 degrees. So the theta is all the way around like that. There's your 210. That's definitely sitting in quadrant 3. Now, what's this alpha thing? Well, that's the reference angle. Okay, so the reference angle is a little helping angle you can use in order to try to find answers to exact value questions. So it's the angle between your final ray and the x-axis, like the quickest you can get back to the x-axis. So 210, well, that's like 180 and 30 degrees more. So just this angle in here, that's the reference angle, 30 degrees. So what I would do at this point is I would start asking myself, well, do I know anything about the trig value for the reference angle? And again, I'm looking at the second consonant. Maybe I'll be thinking about sine. And so it might be super helpful to say, well, you know what? I know that the sine of 30 degrees is 1/2. Okay, great. That's going to help me out. So if I was to try to find the sine of 210 degrees, I know it's going to feel a lot like doing the sine of 30 degrees. It just might be wrong by a minus sign. So I can already like put the half in there, and then I can look at it and go, okay, quadrant 3, is sine going to be negative there? Oh yeah, sine is about y values, so it definitely will be. So I can go and just add my own little negative in there. So the sine of 210 degrees is actually going to be negative 1/2. The sign of the reference angle will always be positive, right? Because the reference angle is a tiny little number less than 90. And now cosecant. Well, again, second consonant, sine upside down. Just take that number and reciprocate it. So there, without too much work, I was able to figure out what the cosecant of 210 degrees is. I can do that game with any special angle. I can find its exact value if I was to do any one of the 6 functions: sine, cos, tan, cosecant, secant, cotangent. It just takes a little bit of time. Okay, next page. Let's switch gears. Let's just go over some geometry calculations that we might have to do for calculus. I'm just looking at some areas and volumes. If you've got a rectangle, obviously rectangles, they have lengths and they have widths to them. And no surprise here, the area is super easy, just length times width. Okay, that one everybody knows. Now, let's get to the ones that people forget sometimes and sometimes want some help on. Well, you're going to need to know these. So by this point now, you should be starting to commit these to memory. For a triangle, if you're going to try to find its area, then you have to think about the base and you have to think about the height. And the area for a triangle is 1/2 of the base times the height. Oops, that was a weird looking H. There you go. 1/2 the base times the height for the area of a triangle. Trapezoids, well, a little bit weird looking. Okay, they've got one set of parallel sides. Sometimes they have the parallel sides going sideways, like this first one. Other times they go up and down. For the first one, I'm going to say that, you've got like one base here and another base there. And then there's a height to this story, like this. The other picture, kind of the other way around. It's got a couple of heights. Maybe I'll call this height 1 and this one height 2. And it's got one base along the bottom. And so if you needed to find the area of a trapezoid, we're going to average the length of those parallel sides. So one option, I could do this with the left one here. I could say, hey, why don't we take the two bases, base 1, base 2, let's average them. Let's add them up and divide by 2, and then multiply by the height. In the other picture, it's going to be the other way around. I could take the base, and then I could multiply by the averaging of the heights. We'll take height 1, height 2, and we're going to average them by adding them up and dividing by 2. Okay, for circles. I know sometimes we joke and say, oh, they're so hard to remember. Yeah, okay, that's nice until now. Now you need to remember these. Okay, so from this point forward, it is expected that you will know how to find the circumference of a circle, that it is 2 pi times the radius, or if you wish, it is pi times the diameter. The area of a circle is pi r squared. From this moment forward, it is expected that at any moment that you'd be able to calculate that. Okay, so start memorizing that now if you haven't memorized it already. For a sphere, like a ball, if you take a look at them, they have a characteristic radius to them. A couple of things we can do with this. The volume of that ball would be 4/3 pi radius cubed. You got to commit that to memory now. The surface area, if you had to paint it, is actually 4 pi radius squared. They're kind of similar, kind of different, those two equations. And at this point, you've got to commit it to memory. For a cylinder, they have a radius to them, and they're also going to have a height to them. If you think about them, they've got a beautiful base that looks just like their top. Okay, and then over here, just drop in a little height measurement. The volume of a cylinder, like it is for any prism, is the area of the base times the height. So pi times the radius squared, that is the area for the circle in the bottom, right? You can see that right up here too, right? But then that gets multiplied by how tall it is, multiplied by h. If you have to find the surface area of this cylinder, if you have to paint it, well, if you think about it, it's going to be one circle plus another circle plus a label that goes all the way around this soup can. And that label is actually beautifully rectangular. It's as tall as the can is, and it wraps all the way around the circumference of the can. So the surface area for a cylinder, you have a couple of circles, so 2 pi r squared, plus this rectangle. The rectangle is 2 pi r for its distance this way as it wraps around the can, and then it's h tall. So this last term ends up being 2 pi r h. It's got to be committed to memory. Okay, let's go over the page. One more row, two more shapes here that we've got to be ready for. If you've got a cone or any kind of prism that now looks like a pyramid, goes up to a point, you pick up a 1/3. So instead of being pi r squared h like it was for a cylinder, there's now a 1/3 in front. That happens for any pyramid actually. And washers. For washers, they have two different radii to talk about. There's the smaller radius, maybe I'll call that radius 1, and then there's a bigger radius that goes all the way to the outside. We'll call that radius 2. And they're going to have some height as well for how tall this washer is. All we're going to do is take one cylinder and then subtract out a cylinder on the inside. So the formula for the volume here is going to be pi, the big radius, let's go radius number 2 squared times h. There's the whole big cylinder. Now we'll subtract out the core. Pi radius 1 squared times h. Now, some people like to do a little factoring. They think it looks a little nicer maybe to extract a pi. Maybe you can pull the pi out front if you want. And we would have second bigger radius squared minus first smaller radius squared. And yeah, there's still an h out there too. So sure, the h and the pi's, they can be extracted. That works. But can I show you something that does not work, that's not okay? Okay, so I'm going to put in here, but not this. It is not okay to subtract and then square. You can't go radius 2 minus radius 1 squared and then multiply by h. Okay, it has to be squaring first and then subtracting. Okay, that's the end of the shapes. Let's talk now about similar triangles. Oh, that should come back here in a second. Maybe it will. Maybe it won't. Give me 1 second here. Sorry, had a little computer glitch there, but managed to get that to come back. That's the end of the shapes that we're going to look at. Now let's take a look at similar triangles. So we've got these two triangles here. We're told that they're similar. Somebody says, oh, try to figure out how big x is. So it's like the smaller one has been stretched in a nice proportional way, and you're going to try to figure out exactly how big that side needs to be for x. And we're going to do this just by setting up some proportionality. And different people like to write this different ways. Some people like to stay within one triangle, and they might say, oh, 3 corresponds with the 4, just like the, and then they go to this triangle. Now, if you start with the bottom side, you got to start with the bottom side here too. And they would say, just like the x corresponds with the 5. And then they would cross multiply. They would say, okay, if I multiply this one cross, that's 4x. And multiplying the other cross together is 15. Okay, great. So x is equal to 15 divided by 4. Fantastic, that's the right answer. Just so you know, other people might look at that and go, oh, that is so strange that you would write that as 3 goes with the 4, just like the x goes with the 5. Half the people in the world would look at this and say, oh, I would have said the 3 corresponds with the x. They kind of go like bottom side this triangle to bottom side that triangle. Then they go back and go, okay, up and down side with the small one, 4 corresponds with the 5. Now you're going to get the exact same answer, of course, right? When you cross multiply, both groups get 4x is equal to 15. It's just that different people see that different ways, and we'll write it down differently. But once the cross multiplication happens, you're fine. Sometimes you might have to throw a little Pythagoras in there too. So this one here says solve for x. I'm going to try to figure out how big that is. Well, I could do a little Pythagoras right off the start and say, well, right angle triangle there, or it looks like it's a right angle. So maybe I'll find out how tall that side is. And I could say, okay, a squared plus 9 squared is equal to 15 squared. And if I run the numbers on that, a squared ends up being 144, and the a ends up being 12. Okay, so this picture is not to scale, obviously, because the 12 there is bigger than that 9, but that's just how it's coming out. Okay, great. Now, I'm going to try to do a similar triangle thing, and it is okay to kind of look at it and say, well, you know what, there's a small similar triangle in here, and then there's a big similar triangle in there, like this. And those two are similar. They have the exact same angles in them. And so we can use that now to figure out how big the x is. So I might do it like this. I might say, you know, the 12, and again, it's not to scale, right? 12 is bigger than the 9, but that's how it is here. The 12 corresponds with the 20. I'll go to the big triangle. So I went orange to pink, just like, and I'll go back to the orange. The 9 corresponds to, now just be careful. It needs to be the whole bottom side of the pink, because the 9 was the bottom of the orange. Well, the whole bottom of the pink would be actually 9 plus x. Okay, this will work fine. Cross multiply and we'll get there. We're going to have 12x plus 108. When I do that first cross is equal to the 20 times the 9 to 180. And this solves pretty quick. So you could go with a little triangle hiding inside a big triangle. That's totally okay. And don't be afraid to use Pythagoras. And don't be totally shocked if you find the scale, like mine here was not to scale, with that 12 actually being obviously bigger than 9 numerically, but not looking like it was bigger than 9 on the picture. That can happen sometimes. So on the next page here, we're going to see a story where there is a little triangle hiding inside another triangle. So example 4, a conical cup has a height of 8 and a diameter of 6. You have to figure out the volume of the cup if water is filled to a height of 5 centimeters? How much water would there be in there? So we're not going to fill the whole thing up. The cup itself, if we had filled the whole thing up, would have been 8 tall. And it says 6 for the diameter. Well, I'm going to think radius. It just kind of works better for my formula. So the radius for the whole cup is half of the 6. It's going to end up being a 3. But we're going to fill this up with some water only part way. We're going to fill it up maybe to here, okay, a height of 5. Okay, and so it's all full of water, right up to 5. So this is going to be 5. But I don't know what the radius is going to be at that spot, because it's not a full 3 centimeters wide there for the radius. It's not a full 6 wide. I'm just going to call that radius at that moment R. And if you look carefully, there's kind of a little triangle and a big triangle hiding inside there. I'm going to mess this picture up for a minute, then I'm going to erase the mess and just redraw it. There's a big triangle, and then there is another smaller triangle hiding inside right there. Okay, now that I've ruined everything, let's go and just take those and put them over on the side where it'll be a little bit more clear. And I think the grammar of the question wasn't perfectly clear either. We're trying to find the volume of not the paper cup itself, but the volume of the water that's in there. So the big triangle, kind of a cross section of the cup, looks like that. That's a 3, that's an 8, and now when we fill it up with water, I really will need to know what the radius of that little cone of water is. And we have water in cross section making a little triangle there like that. This is a 5, but I don't know what the radius of that little cone of water would be. But we can find out. Okay, that'll fall apart pretty quick. We can just do a similar triangle. The R corresponds with, now some people might say 3, some people might say 5. You can do it either way. Maybe I'll go with the 5. So the R goes with the 3, sorry, the R goes with the 5, just like the 3 goes with the 8. And some people might have the 3 and the 5 in reversed places there. It won't make any difference at all once you cross multiply and you have 8R is equal to 15. And so R is equal to 15/8, or 1.875. Okay, now the volume of that cone. All right, I've got to know all my volume formulas for a cone. It's 1/3 pi the radius squared times the height of the cone. So that cone of water, if that's what we're trying to find the volume of, 1/3 times a pi times this 1.875 squared times the height of 5. Now, you can just work that out as a decimal. There's nothing wrong with doing that, right? You can take your calculator and say, okay, as long as I go to 4 decimal places, I'm fine. So 1/3 times the pi times 1.875 squared times 5. It's an irrational number, but if you want to, it is totally fine to say, well, watch this. Here, I'll give you 4 decimal places. 18.4077, and I don't even have to round that 7 up to an 8 in AP Calculus, as long as I've gone 4 decimal places deep. Here's another option. I kind of like doing this. You know, it's the pi that's messing everything up. So what if I had done that again, but this time I'm not going to put the pi in there. I'm just going to kind of keep that for later. So eventually I'll still have to multiply this by pi, but I get this number here. Now it's a little bit awkward looking, but it's probably actually a reasonable fraction. It's a rational number. So I could ask my calculator, hey calculator, can you go and convert that to a fraction? So I hit the math button and it says, yeah, here, convert to fraction. Yeah, could you do that? It says, yeah, that's just 375 on top of 64. Didn't you know that? And it's like, yeah, no, I didn't know that. So I could write this as 375 on top of 64, but that doesn't have the pi in there. So I just say, oh yeah, don't forget, multiply by pi. And that's just a kind of a cleaner way of writing the answer. It's not required. It's just an option that you can do if you like. Okay, we're going to finish off with something actually quite easy. Proportionality questions. You've probably never seen these before as something that you're asked to do, but they're actually pretty easy to do. And we're just going to do these just on the job training, okay? Just kind of learn as you go here. This first one, I've got two statements that are basically the same thing. It says the quantity W is proportional to the quantity Q. I don't even really know what W and Q stand for, but it doesn't matter. People might also say, oh, the quantity W varies directly with the quantity Q. So those two statements are two different ways of saying exactly the same thing. That second one does have a little shorthand notation that you might see people use. They might say, oh, W varies directly with the quantity Q. They might take that statement there and say, oh, we can write that like this, W, and then they use the Greek letter alpha to say it varies directly with, and then they would say Q. Okay, so great, that's fine. Here's the plan with these. These are just like cookbook deals. You follow the recipe and you're done in 3 steps. First step, we're going to go and write down that proportionality as an equation. And so sure, we can use the little Greek letter alpha and say, well, it kind of follows Q, but if you really wanted to know how to calculate it, we have to throw in something called the constant of proportionality. So I could write this as W is equal to, and then here comes this constant, K, multiplied by Q. Okay, and so it does have an official name. This K is called the constant of proportionality. And as soon as you see, back in the original question, when you see people saying this phrase here where they're, is proportional to, you're going to find that that translates to equals K times. Right? So yeah, W is proportional to, okay, it's equal to a constant of proportionality times the quantity Q. So great, step 1's done. Step 2, let's go and figure out what the value for that constant of proportionality is. So they're going to give you a little information that you can use to extract this value for K. So step 2, they're telling me right here, here's where I'm going to do step 2. Like, oh, they'll let you know that Q actually is 8 when W is equal to 20. Okay, fantastic. So I'll just substitute those in. W is equal to 20. That's equal to some constant of proportionality multiplied by this Q value of 8. Fantastic. It looks like this constant of proportionality is going to be 28ths. Okay, or if you wish, 2.5. All right, now we get to use that over and over. So step 3, maybe I'll rewrite this proportionality equation. I can say, oh, W is equal to, I don't have to say, oh yeah, some constant that I don't know. Hey, I've got it. Here's the constant of proportionality multiplied by the quantity Q. I'm now ready to do this for any setup that they're asking me about, and here it comes right here. They're like, well, can you go and figure out what's going on for W when Q is 50? Sure, super easy. W would be nothing more than 2.5 times 50. Done. Answer is going to be 125. So we're just doing these just by on-the-job training. Let's look at 2 more situations on the back of this page here, and we'll finish up with them. But it'll be the same plan, 3 steps. Write down the proportionality equation. Step 2, find the constant. 3, let's use that to solve some sort of problem. So this one's a little bit different. The voltage V near a charge varies inversely with the distance from the charge, and they call that R. Okay, whatever. I don't even need to know anything about physics to be able to write this down. Step number 1, if I want to write that proportionality down mathematically, they have said that voltage V varies, okay, so I can say varies. Now it says inversely, so that's upside down in the fraction with the distance R. Okay, so there you go, there's your inverse, right? It's down in the bottom, right? So yeah, inverse. Okay, be nice to write that with a constant of proportionality in there. So how about this? V is equal to some constant of proportionality multiplied by 1 over R. Okay, step 2. let's go and find the constant in this situation. So I'm going to go and run some numbers here. They've said, oh, the voltage hits 200 when you're 5 meters away. Okay, now times 1 over r is the same thing as on top of r, right? So maybe I'll put the 5 down there. Whether you write that as k on top of 5 or k times 1 over 5 doesn't make any difference. Constant of proportionality ends up being 1,000. And now step 3. Let's just use this over and over. We now have a really cool equation. V is equal to 1,000, our constant of proportionality times 1 over r, which, yeah, of course, same thing here, right? You can write that as 1,000 on top of r, same thing. But now they're saying, well, can you use that, please? Can you go and find a value for r? Can you find the distance where the voltage would hit 120? I don't need to know anything about the physics. I can just start substituting stuff in and saying, yeah, sure, here, I'll find your answer, 1,000 divided by r, and then we solve for r. This one ends up being 8.3 repeating. And again, AP Calc, if you're going to write down a decimal that does not terminate, you have to go to 4 decimal places. Last one of our on-the-job training, another physics story. But again, you don't need to know anything about physics to do this. In fact, maybe the less you know, the easier it is. The electric field E near a charge varies. So as soon as I see that, I can start writing down my proportionality equation. So electric field varies directly with the size of the charge Q and inversely with the square. Oh, it's got a couple of things going on. No problem. We'll blend it all together. So it varies directly. So that means up in the top of the fraction, right? And then inversely, that's going to be down in the bottom of the fraction. So directly with Q, but inversely with, is it the radius? Oh, no, it's the square of the radius. Okay, right? They said that. So it varies. Put it up on the top, Q, and inversely put it down on the bottom. It doesn't say just the distance, it says the square. Okay, so that's like that. Or if you want to bring in your constant of proportionality, you can say it's equal to some constant K multiplied by Q, all divided by R squared. Now it's just kind of random luck that K is also the letter that physicists would use in this situation, but that's just luck. 2. Let's see if we can go and find that K. So they've got some information here. Hey, the electric field hits 1,440. I don't know what K is. I kind of want to know when Q is 4 and the R is 5,000. And that number needs to get squared. Okay, well, when you solve that, you end up with a K that's really big. It's like 9 with 9 zeros. 9 times 10 to the 9. Well, now I can use that equation over and over. So part 3, here's your math story. The electric field is actually equal to this constant, 9 times 10 to the 9. That won't change now. Multiplied by whatever Q people have got, that's up in the top, and then the radius squared. And then they're saying, oh, well, can you use this to find the electric field? Q might be 3 and R might be 2,000. Oh, yeah, easy. Here we go. Got my 9 times 10 to the 9. Q is 3, and R is 2,000. And that has to get squared. And the answer for that, it terminates, so I don't have to write 4 decimal places down, 6,750. So it's just 3 steps. Write down the proportionality. Step 2, use the full information to find the constant of proportionality. And then 3, just go ahead and use it. And that wraps up a whole bunch of little tiny bits of things and information that we're going to need in order to be ready to do some calculus in the next chapter.